look, it's an alcohol. I know where it's going to react. I know what's negative and I know what's positive. It's just a question of reading it. It's not a question of memorizing everything. It is a terrible thing to have to memorize 500 to 600 reactions individually. It's like instead of learning to read the book, you're literally going to memorize the text. That's harsh. But I'd feel so much better if you guys were able to read it and become more comfortable. So memorize those 20 things. Not for me. I'm clearly hopeless, but for yourself. It'll make this course easy. It'll make things you're going to do down the road a lot easier. So I'm going to be starting, if that's all right. I'm going to do it anyway, even if it's not all right. And we're going to look at the stuff I talked about before, and hopefully this will make a little more sense because you do have a little more background. All right. So you saw this before, so bear with me. Organic chemistry obviously is the study of organic compounds. That is, materials that contain carbon. Why is it so important? Because carbon is prevalent almost everywhere in structures. And the basic rules to figure things out, if you're doing reactions, if you're looking at reactivities, is everything has a specific number of bonds it requires. The four big ones are carbon is always 4, nitrogen is always 3 requirements, oxygen is 2, and hydrogen is 1. If they have fewer, if they have greater bonds, you've upset the bonding and you'll have a different kind of charge. And I'll talk about that down the road. All right. So, reaction types. And I went through this before, but just to recap. Number 1, by a lot, is substitution. This is easy. You're replacing something with a component that has a stronger or larger charge. If it does not have that bigger charge, it's not going to displace anything. You've mixed the things together. That's the end of it. You just mix things together. Nothing happens. It's weird. Elimination is conditions are strong enough to get something to leave, but there isn't a convenient thing nearby to grab onto. Remember, these entities, these molecules have no loyalty. They require charge stability. So if it loses something and it still needs 4 bonds, it'll just form a double bond to make up for the missing item. Or if it's missing 2 things, maybe it makes up a triple bond. But one way or the other, carbon's going to have 4 things, nitrogen 3, oxygen 2, etc. So it's not a question of guessing. It's a question of reading it. Mechanisms. All the number 1 mechanisms are called 1 because there's only one main component. They're considered to be monomolecular. What we've done is alter the conditions. We've made it unstable enough that it will have a reaction without that full separate entity. All of these 1 monomolecular mechanisms go through a carbocation. To refresh your memory, a carbocation is a carbon with a positive charge. How does it form? It tends to form in acidic solutions, and it's like this. The carbon's bound to 3 things, but it's missing that 4th. And for a brief nanosecond, it makes a tiny positive charge. That is unstable. There's only 2 ways for it to achieve stability. Grabbing onto a nucleophile if they're nearby in sufficient concentration, or forming a double bond to make up for the missing electrons. Those are the only choices. So we often say they're competing reactions because that carbon wants stability. It doesn't care if it binds a nucleophile. It's inert chemicals. It has to have stability. It will grab a nucleophile if it can. If it cannot, it will form a double bond. So the reactions are competing only in the sense that the carbons want stability. Alexis, is that making sense or am I freaking you out? A little of column A, a little of column B. Any of the things that say a 2 mechanism mean it's bimolecular, 2 distinct components, 2 completely separate charged entities are involved. In general, reactions occur when there is a stronger, larger, quote, more powerful charge coming in. And if it's not bigger, stronger, more powerful, it's not going to react. You can cry at it. You can try to order it online. Nothing's going to change. Bigger charge or nothing. We can help slightly weaker things react by altering the conditions in the reaction mixture, in the solvent. And one of the common ones we do is we add protons. We acidify. If we add enough protons, it tends to form carbocations. So acidifying reaction mixtures is a very common process in organic chemistry. You guys okay? You okay? I haven't seen you without your Slurpee today. Are you all right? You doing okay in there? Just got to check here. I got someone not signing in all right. Let me see if I can figure this out. Give me a second here, you guys.
It's actually me. Sorry.
Are you in? Looks like you're in. Very strange. All right, sorry. Let me keep back. Where was I here? Oh, yeah. We alter the conditions to favor reactions. What do? We can increase charges by acid. We can increase concentration, so there's more intermolecular collisions. We can even, do what I talked about in the lab. We can certainly change the pH, not just for protons, but to make certain components negative, certain components positive, or certain components neutral at their isoelectric point. All of those are things we do to the solvent, to the molecular environment, to change the reactivities. I'm going to talk about solvents if I get that far today. Not too likely, but I just want to let you know. Nomenclature means naming. And I keep telling this to you guys. Memorize those 20 basic group names or try to learn 600 reactions. That's just a horrible thing to do. I don't mind you suffering, but that's just generally too much suffering for anyone, in my opinion. So, the types of reactions are based on what happens. Whether it substitutes, whether it eliminates, is often based on the incoming group. The incoming groups are either negative. Everything negative we lump into this big name called a nucleophile. Everything positive coming in we call an EP or electrophile. It's just a terminology. You could name it as a hydroxyl. Fine, I know that's negative, I know that's a nucleophile. But when you're just referring to it generically, anything negative coming in is an Nu minus nucleophile. Anything positive coming in is an EP plus electrophile. The basic rule is unchanged. The basic rule is positive things, hello electrophiles, attack negative areas. Avik, is that okay? Because I could be lying. You don't know. I mean, I wouldn't trust me. Nucleophiles, negative things, will attack the most positive area. So here's the secret sauce. Most of the things we're looking at are carbonyl structures. A carbonyl, C-A-R-B-O-N-Y-L, a carbonyl structure has this in it. Something over here, something over there. Here's the carbonyl structure. Carbon, double bound to an oxygen. And here is why a carbonyl structure is important. The molecule, before anything happens, has some inherent, that is innate, instability. The oxygen is highly electronegative. It is pulling electrons from the carbon. It's not getting them completely. It's literally pulling some of the electronegativity. That's fine, like that. Ooh. Pulling some of the electronegativity from the carbon. What does that do? It makes this oxygen ever so slightly more negative than everything around it. It makes, as a consequence, by pulling electrons away from carbon, it makes the carbonyl carbon ever so slightly more positive. But that means, compared to everything else in this molecule, in this compound, you've got a negative area. That's where positive things are going to attack. There's nothing to figure them out. Read them and weep. Any electrophile will go for the most negative entity, period. Any negative entity will go for the most positive. Straightforward, nothing to do, just look at them. Every time you see a carbonyl structure, you know positive things are going to attack here. You know negative things are most likely to attack there. Now, If you have different functional groups with bigger charges, that might change things. But just looking at this section of a molecule, you know what it's going to do, and you know what's going to attack it. There is very little variation here. So SN1 is shorthand for substitution with a nucleophile, something negative coming in, and it's monomolecular. So it probably went through that carbocation. E2 is an elimination by an electrophile, but it was bimolecular. Two charged distinct entities were involved. And as we go through this course, you're going to see examples of both of these. But I just want to lay the groundwork for this terminology. I look at a functional group instantly, and I know where this molecule is negative and where it is positive. I know where the reaction is going to occur. There's simply nothing to figure out. If you don't do that, organic is a pretty scary thing. If you're going to just try to brute strength memorize these, it's a tough way to go. Anissa, have you been memorizing everything so far? I know what you're thinking. Shut up, Dave. I will not. I'm literally paid not to do that. All right. Just to go over the rules again for naming. There's 278. In fact, if you pull out the big manual, it's like a couple thousand rules. Here's the best thing. Most of them are pretty stupid, just telling you. The reality is you can name most things with the 4 fundamental rules. And I told you this before, but allow me to say it again. Most of the rules will work. Some of them will not. You're going to only try to make it work out. When you're naming things for me on tests, as long as you tell me what to do and I can write it out and it makes sense, I'm not going to care that the numbers don't go from smallest to biggest. I'm not going to freak out if it's non-alphabetical. I'm concerned about the accuracy and the safety of what you're naming. So that's really my focus. First thing we do, we always look, I do this instinctively without even thinking, what is the longest chain of carbon exception that has the most important groups? That is the functional or charged groups, the higher priority groups. And the short version is the higher priority groups are always the ones with the special charges. So by definition, figuring out your parent chain is telling you what kind of compound. Is it an aldehyde? Is it carboxylic acid? And by knowing that, you already know where the reactions are going to happen. And again, we're going to go through these things eventually. This is all sort of precursor. I'll break it down, strike by strike. If you have to number your side chains, in theory, you try to keep the numbers low. Not always going to work. That's okay. If you have a group that appears multiple times, 2 methyl groups, you would say it is a dimethyl. Is that true? How do you know I'm not lying? Carlo, I could be lying. I don't know. I can't tell either. I'm trapped in me, and I don't know. If you have side groups in different ones, you try to put them in alphabetical order. Again, it isn't always going to work, and particularly when we're looking at plant, like pathobiology, we're looking at all sorts of complex natural products, it gets really hard. And in those cases, almost everybody only will ever use the trivial names. And I will show you later some of these plant-based compounds. They're a paragraph-long name. They did it in the original paper, and they've never used it since. So be advised. When you number, you try to have the lowest number, your highest priority groups, if you can. You try to have the lowest number for double and triple bonds, for lower priority groups, and for the first name group. And I'm telling you outright, sometimes not all of these things are possible. Don't freak out. Just count them accurately. I had used this as an example before. This is where you guys started getting all woggly-eyed, which isn't even a word. Andrew, is that a word? Woggly-eyed? It's from the Blictionary. I know, I wrote it. So when I look at this, I can see 1, 2, 3, 4, 5. Woo, 5. But I want to include this guy right here. So the habit you need to be in is ignore the carbons at first. Identify charged groups. Hydroxyl group. Right away, that's telling me we've got 2 negative areas. No matter what, I have to have those functional groups in the parent compound. Period. You could have a chain 700 carbons long. This one wins. The ones with the charge groups that are far more prone to reactivity are the highest priority. They're the highest priority for naming. They're the highest priority for reactivity. Let's count them up. Hydroxyl, hydroxyl. 1, 2, 3, 4. Or you could go 1, 2, 3, 4. And I mentioned this before. You really need to number these on a piece of paper. It is heartbreaking for me to have to mark something wrong, a simple name, because people couldn't count. I have repeatedly had to mark wrong methyl groups. How do you count to one wrong? Ethyl groups. So please, give me something to work with. It just freaks me out. 1, 2, 3, 4. What is it? Methyl, ethyl, wethyl? What's after that? Wethyl?
Propyl and butyl.
Really? That's way better. Do you want to teach the course for me? I'm just going to go back there and sleep. No? Okay, fine. You're right. Methyl, ethyl, propyl, butyl. 4. And I can see it's alcohol, so I know it's a butyl alcohol. You could say it's a butadiol. You could say it's a diol butane, although people don't often do that. So that takes care of this chunk. However, we do have to name these guys. So if I'm starting here, 1, 2, I can see there's a 2 methyl ethyl, 2 ethyl. Al, is that legitimate? I don't know. 1, 2, 2 ethyl, 1, 2, 3 methyl, 2 ethyl, 3 methyl. But then I got to name these incredibly important bits. 1, 3 butadiol. You could say buta 1,3-diol, and I'd say that's right. But what you have to do is number where these are. I will not give you anything ever harder than this in any testing. I'm going to keep it simple, and I'm going to keep it on track, and I'm only going to test you on things that are in the handwritten notes. I'm not going to do a bunch of weirdo references and surprise you, unless you like surprises. Dr. Henderson, do you like surprises on exams? How many of you like total surprises on exams, where the prof says, I'm testing you on this, and then they give you a doctorate thesis? You guys want like a doctorate thesis? Yeah, let's vote.
No,
yeah,
you're good.
Oh, you can talk. Okay, great. Yeah, honestly, I'm going to stay dead on the money. I'm going to take these things you're going to draw from things we've looked at, okay? No surprises. You don't deserve that. All right, so this is harder than most of the stuff you're going to see. So I went through this again, but using the, can we play PlayStation? Can we play PlayStation? Can we play PlayStation? Can we play? Using the nagging technique taught to me by my sons, I'm going to go over this once again. And I'm going to say every one of these like I'm channeling myself as a 17-year-old surfer valley girl from Malibu, California, which I was in a former life. It was very cool. All right. Alkanes, well, carbons, boring. Alkenes, double bond. Alkynes, 1, 2, 3, triple bond. Notice in each of these carbons, no matter what, how many bonds do they have? 40. Who said 40? Eugene, was that you? Oh, 4. Okay, that's way better. Alkohalides, RX. Like a question. Carboxylic acids, RCOOH. How am I doing? Am I close? Nitriles, CNN, just cut off one of those C's right there. Amines, R, N, blah, blah. It could be hydrogens, usually is. It may be something else, depending on what we're working with. Alcohols. I don't want to frighten you, but I once had a student who claimed they'd consumed alcohol. That's crazy talk. ROH. Aldehydes, R, COH. Ketones, R, COR. Ethers, lions roar, ROR. I do hope you're memorizing these in real time, Dr. Herring. All right. Esters, RCOOR. Is that true? I hope so, because it's going to help you on an exam. And amides, RCON, da 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 da. Now, one pet peeve of mine. Amines are NH2. Amides are a carbonyl compound with a C and a double bond O. Important difference. I've seen people toss those words around, but yeah, there's problems. Make sure it's right. All right. Benzene is the lovable stop sign of organic chemistry. It is different than everything else because it is sharing electrons in the center. Now, we call things benzene something if the benzene is the parent compound. If the attached group is more important, bigger charge, we then say it's a phenyl ethanol. Benzyl means the benzene is the most important part. Phenyl means it's a benzene attached to something that's more important. Phenyl ethanol. Now, phenol sitting right here, ready for this? They made up the name. It is off in space by itself, which is why I've included it. They simply call it phenol. It is my sad duty to report that. So, yeah, try to apply the rules to that. It doesn't really fit. So they just call it phenol. If you work with this in the lab, you will know it smells extraordinarily bad. If you touch it with your skin will turn white because it'll oxidize it, which is less fun than it sounds. An exception to all the rules, ready, is benzyl alcohol. They literally made this name up. It's carbon attached to an alcohol with two hydrogens, CH2OH. By agreement, not by any kind of rules I can follow, it is called benzyl alcohol. Sorry to report that. It's just the way it is. It's one of those weirdo things that all the rules ignore. Examples I went through before. Well, I'm counting this up. I always count first. 1, 2, 3. Methyl, ethyl, wethyl. It's correct, isn't it?
Propyl.
Propyl. You guys going to keep like nagging me? See, once you're nagging me, then you're probably onto it. All right. Methyl, ethyl, propyl. So I can see it's propyl, propane, but I can tell right away it's alcohol. No matter what. You could call it propane alcohol, but most organic chemists I know, Rim, are super lazy, so they just like squish it together, propanol. I mean, do you guys want to write extra consonants? Alex, are you yawning? You should learn to yawn behind your arm, like you're, wiping away, like I do, like soup off the mustache or something. All right. So 1, 2, methyl, 2, propanol. Are you guys good with that? It's not like these are the only examples you're going to see. I mean, this is a course on this. There's going to be lots. In this case, it tries to trick you by looking like benzene. It is not. This is a 1, 2, 3, 4, 5, 6. It is a hexane, except it's not. It is a cyclohexane, but I can see a double bond. Therefore, it is a cyclohexene. Ene for the alkene or double bond. Cyclo, because it's in a circle, and is 1 methyl cyclohexene. If you were to submit this to me and not put the 1, I would draw the methyl group on one of these anyway. It's typically assumed to be there, but if you're ever not sure, my advice, write down the numbers. You're never ever going to be wrong writing down the numbers. You're never going to lose marks writing down the numbers, and it's pretty hard to miss. Just saying. Hang on. I'm going to have what's in Dave's Mystery. What do you think's in this class today? Look at that. Is that Victorian bitters from a sleazy pub in Sutton, just outside of London? Oh, it's really awful. Tastes like cyanides. Okay. The ISO prefix does not mean the International Organization for Standardization, although it does, just not in this context. ISO means an extra carbon. It's telling you both about the chain length and that extra methyl group is attached to the number 2 carbon. Take a look here. ISO means extra methyl of the number 2 carbon. And it implies, and this was done by a whole bunch of organic chemists arguing for years, it implies the carbon chain length is 1 longer than the longest continual chain. So this is attached to something else, we don't care. But this whole group is an isopropyl group. There's a methyl group, 1, 2, and in 3, so 1, 2, 3 is propyl. Isopentyl group, 1, 2, 3, 4, we would probably call that butyl. But on the number 2, there's iso, it's a methyl, it's an isopentyl group. You could also call it 1, 2, 3, 4, a butyl group with a number 2 methane. But most folks, and I know specifically in your instrumentation, are going to do it this way. So be aware, you should expect, you might want to write this down, expect to see a few iso compounds in your instrumentation. I don't know if you'll see them this term, but you might start to see them. Isopentyl groups, isopropyl groups, and isobutyl groups. And here's an isohexyl group. 1, 2, 3, 4, 5 is pentyl, but when you're using the word iso, it means it's 6, hexyl. Iso, carbon number 2. It is a quirk of naming, and it was done largely because some of the instrumentation you're going to work with will get you very different responses because of that weird sort of T shape. I'll let your instrument guys explain that to you, but just be advised. I'm not going to spend a lot of time doing this or throw these at you, but I do know, particularly in your advanced instrumentation, where they give you 10 tubes of unknowns and a term to figure it out, it's going to show up. So remember, if you're getting weird numbers and some of the stuff works, some of the stuff doesn't, it could very well be that hidden methyl group in an iso compound. Next version, and again, I won't use this much, but I absolutely guarantee you're going to see this, particularly the butyl groups. Sec means secondary. Tert means tertiary. What it means, the attachment carbon right here itself is attached to other carbons. Here it is, look, 1 carbon it's attached to 2 carbons. That doesn't name it. It just says it's a secondary butyl compound. It means there's 4 here in total. The attaching carbon is itself attached to 2 other carbons. Carlo, does that make any sense? Is that? You're on Etsy right now? Cool. All right. What? No? You're downloading Steam games because of the sale? You didn't hear about the sale? I see. Tough crowd today. Rim, you know you're signed in twice, eh?
Yes.
So I'm going to have to divide the marks between 2 of you. Oh, well.
Well,
In this case, 1, 2, 3, 4, 5. This is a 3-ethyl propyl group. It is tertiary. Why do we say that? Oh, no, sorry. It's not secpentyl, because this, in the center, will always give you the same compound, whether you flip it around or not. So this compound, flipped 100 degrees, doesn't do what my hand does, it's exactly the same material. 3-ethyl propyl group. Now, how far did I get before with you guys? That's where I stopped, right? How communicative you are. Wiggle your eyebrows.
yeah.
Try blinking in Morse code. ... beep, ... Okay, who swore? Okay, let's talk alcohol. I think that's where I stopped before. Is that where I stopped or no? No, I think I might have done this before, but I want to make sure you get this. Alcohols are literally the perfect point to start talking about chemicals and reactivity. They show up in a huge number of syntheses. They always obviously have hydroxyl groups as their highest priority, ROH. And shape-wise, they're almost identical to water, 120-degree bond angle. That is planar. You guys care about bond angles, don't you? Dr. Salazar, you care about bond angles, right? Bond angles? Oh, yeah, wrong one. So what do we have here? Don't memorize this. I picked a small example. Why are these so important for analysis and for industries? Because we can make all sorts of stuff into alcohols with almost no effort. Epoxides, esters, aldehydes, ketones, alkyl halides, alkenes, to name some, all can be converted with no effort into alcohols. From alcohols, we can make all sorts of other very specific compounds. It is a key and very important industrial intermediate. Other ethers, other alkyl halides, inorganic esters, organic esters, alkenes, aldehydes, all sorts of stuff. So if you're ever sitting stuck at a train, have any of you ever been stuck in front of a train where it's only supposed to be like 4 cards long and it's 180 cars, and you're sitting there and your phone's out of juice? I'm still angry. Although I can read the signatures and the signage on the sides, it is stunning how much alcohol for industrial purposes passes through Winnipeg and is carried on trains. Next time you're stuck there, phone isn't working, have a look. All right. Are you ready for today's secret sauce? Secret sauce. These properties of alcohols really are properties of organic chemistry. I'm using alcohols as a specific discussion point, but all of these factors come into play everywhere else. You need to know this. If you add protons to something, what's the charge on a proton? Help me out here. I've only got a rental brain. I should have spent it.
Positive.
Positive.
Are you sure?
Yes.
Yes.
No. Look, I set you up. Your answer is
Oh,
I'm positive.
positive.
That was the joke. Man, you guys are bad at this. You are not going to be there on open mic night, let me tell you. All right. So if you add protons to a solution, what is something going to pick up? Okay, if I feed you chocolate cake, what are you going to eat?
Chocolate
Okay.
I would have said protons because I'm a jerk, but yeah, chocolate cake. So if you add protons, what is the material going to pick up?
Protons.
Positive charge.
Chocolate cake. Okay, right, fine. So it'll pick up, even if it's only transitory, a proton. And we call this an oxonium ion. It has its own name. Here's the kicker. Ready? Hey, Dave, wake up. Isn't that H2O, world's best leaving group? Oh, dude, you're right. So by adding protons, you are setting this up to form water, one of the things on planet Earth that is dying to form. So just by adding protons, they'll pick up proton. Boy, pretty obvious. If you add base or put it in base, strong negative charges are going to strip away positive proton. If you pull away that proton, you've got a negative ion. That is, and there's a name for it, an alkoxide ion. And this doesn't just have to be alcohols. Anything with the capacity to grab a proton, anything that can lose a proton will form a negative ion. And it's really you, as the organic chemist, who's setting up and deciding what are those charges going to be. You're deciding what's going to happen. You add protons, you add acid, it forms an oxonium ion. Fantastic leaving group. You're all ready to do reaction without trying. If you add base, you can strip away that proton. Proton's positive, poof, it's gone. You've made RO negative. It's an alkoxide ion. Super easy. And that applies obviously to alcohols, but to other things as well. None of the organic am I teaching in isolation, nor are you learning in isolation. Although I am pretty interested in that chocolate cake part I was talking about. Probably should have had more lunch. All right. One of the things alcohols can do, like so many other materials, they can form hydrogen bonds. They're not very strong. They're puny little tiny things, just like your instructor's mind, just microscopically small. However, they always show up with, say, 4 million friends. And with 4 million friends, suddenly it's on. And as a consequence, even though they're 10% the strength of a good old covalent bond, there's lots. So many, in fact, it increases the melting point and boiling points of alcohols, or, secret sauce, anything else that can form hydrogen bonds. For example, if any of the chemicals we work with can form hydrogen bonds with a solvent, like water, boom goes the melting and boiling points. So you're changing physical properties by these lowly, little, insignificant intermolecular forces. Van der Waals forces, we call them. Yes, they're tiny, but there's a whole lot of them. Polarity. This is going to, surprise you. If you're doing extreme yoga, it probably won't surprise you. Extreme yoga is when you take your arm and fold it behind your back and then all the way around your front a couple times. That's pretty extreme. Most chemicals can't do that. However, the shape counts. The shape counts, and I'm using this as an easy example, because it changes how things can access the reaction site. If you can't drive in there, if there's 300 truckers in Ottawa blocking your way to the beer store, we call that steric hindrance. I should go there and solve this. They wouldn't like what I do. That's steric hindrance. You've got parts of the molecule in the way. On the other hand, look here, ROH. Well, I think I said oxygen was electronegative. That hasn't changed. So this electronegative oxygen, see this little tiny S? That means the oxygen is pulling electrons from its buddies. It makes this carbon or R group, alkyl group, ever so slightly positive. It's also making this hydrogen ever so slightly more positive than if it wasn't bound to an oxygen. But what that's saying is, look at that. It's a polar molecule. The charges are not distributed equitably. This end is more negative. This end is more positive. That means in solution, it's going to start orienting itself based on the way the positive and negatives of its neighbors are oriented. Everybody figures if it's in a liquid, it's random. Nonsense. It's random if nothing has any charges, period. If it has shape, and if it has differential charges, even if they're very, very tiny, it is going to interact. And we say it has electrostatic, underlined in blue, interactions. That means it has interactions and behaviors caused by those charges. So that means the solution of alcohol, just like a solution of water, the molecules are going to orient themselves. It is not a random event. That means they change their shape, it will increase melting point and boiling point. That's MP, Member of Parliament, and BP, Hayden Powell, something to do with the Boy Scouts, but I don't know. All right. Secondary alcohols, because of their weirdo shape, and we'll get to this later, are more polar than primary. I got to it right here. We've got our alcohol, two things attached. It's 2-propanol, and we have 1-propanol. Why? Because this one, you can just drive here all day. Here, it's got a trucker blockade, and getting to Rideau Hall is much more difficult. Have many of you been to Ottawa before? None of you have gone skating on the Rideau Canal? Okay, spring break, we got to have like a field trip. We'll go there, and then we'll go to Quebec City and stay in the Frontenac Hotel, which is really haunted, but also very cool. I'm just going to have to convince the dean that I need some research money. It didn't go well last time. Questions or thoughts? These are important points. Let me do this again. Put anything in acid. That's protons. If it can, we'll pick up protons. It will form an oxonium ion. In this case, it can make water a superb leaving group just by adding protons, just by acidifying. You're setting it up. It's that easy. If you add base, you pull away protons, you leave a negative ion. We call that an alkoxide ion. How do you make it? Put in base. Here's the big shock. You put in positive things, the thing becomes more
Positive.
Positive.
I was looking for chocolate cake. You put in negative things like base, it becomes more.
Negative.
Negative.
I was going to say positive, but I'm a jerk. You guys are all right. Fine. Okay. The other property is they can obviously form hydrogen bonds. You got a molecule with hydrogens, to some extent, greater or lesser, it will have the capacity to form hydrogen bonds, period. So get used to that. That changes properties. It is not a random solution. Its shape and charge distribution will also affect its behavior in many ways. We call the charges electrostatic interactions, that is maneuvering based on charge. Here's the secret sauce. If you've got polarity and you've got electrostatic interactions, you've also got places for the reaction to happen. Electrophiles, positive things, you already know what they're going to do. There's no surprise. You know where negative things are going to go. There's no surprise. And although this is a simple molecule, this could be 80 carbons long. It's still going to behave the same way. Just practicing. Anissa, you're still conscious? I used to sit in a chair and I used to run a broom up the back so I could stay vertical. I didn't actually. It's a good story though. All right. This is what I was alluding to and you are ignoring in the lab this week. Oh, by the way, what is the structure of an ester? RCO. It'll get easier next year or the year after. RCO.
OR.
Chocolate cake. Okay, fine. So solvent is a liquid that dissolves another compound. One thing I do have to warn you, the more organic chemistry you do, the worse your spelling is going to become. I'm not sure how you spell dissolves. I know there's an S. There might even be 3, but just to be safe, I've included 2. Are any of you sure without using spell check? What's that? You have a spell check generation? Fine. 3, I like that. Okay. Any liquid that dissolves a solute or other compound is a solvent. The work we do in organic chemistry is conducted in solvents. We don't hurl dry chemicals around the room. Sure, I'd love to, but Braden gets real cranky. Holy smokes. So we're going to use solvents, and the choices of solvents is important. It makes things happen. It makes things stop. It makes things go at a certain speed. The choice of solvent is the venue that the band is going to play in. It's important. The 3 main properties, and there's a whole bunch of peripherals, but the 3 ones you cannot live without. Is it protic? And you can also ask yourself these questions about the chemical that you're putting in. That's a secret. Is it protic? Can it form hydrogen bonds? Oh, that's important. Protic solvents have the capacity to form hydrogen bonds with anything you throw in there. Oh, that's important. An aprotic solvent, or non-protic, but they do call it aprotic, can't do that. How do you know what they are? You can look them up online. You can look them up in the CRC Handbook of Chemistry and Physics. Lots of people have worked this out. It is not your problem.
So water is protic.
Maybe. I don't know. Is it? Is it? Chocolate cake? Yes.
Yes.
It's protic. Yes, we literally just did that. All right. Polar. Polar means, does it have differential or asymmetrical charges? And what we mean is it capable of making electrostatic charge-based interactions with the solute? Apolar materials cannot do that. So just by picking your solvent, you're setting this up to do certain things and to not do other things. Finally, the solvents could even be a donor. You could pick one that has unshared electron pairs. It could donate to help start a reaction. Also a good choice. Non-donors, no free electrons, forget it. Go get your own chocolate cake. So they could be protic, form hydrogen bonds. They can be polar, asymmetrical charge distribution. They can interact on the basis of positive and negatives. And finally, they can be donors. They could even donate entire electrons to a reaction. The general rules, there's always exceptions. I'm not going to go into those. If it has an exposed oxygen, hydroxyl, nitrogen, NH, or F, it tends to be a good solvent for compounds that have the same groups. What? Like dissolves like? Yeah, it's totally true. Right? So it's not rocket science. Non-protic, that is aprotic, has no exposed oxygens or hydroxyls, nitrogens, NH, F. Therefore, it's a bad or poor solvent for solutes, for compounds that have these groups. It's not a hard thing to do. You look it up. Polarity has its own math. I'm not going to go into the math. Rim, you'd be yawning all day if I did, so I'm going to spare you. Hey, wait, Rim, there's only one of you now. Did you kill the other one?
No.
Wait, hang on. Are you twins? Which one is the evil twin? You can tell us.
The one with that picture? Or the
Well, the evil twin would blame the other one, though. Oh, tough. Okay. When we say polarity, we use this tiny little letter called mu. So I have to ask your opinion overall. First of all, is it mu or mu2 that's stronger? Dr. Salazar, look at you acting like you don't know what I'm talking about. I like mu2 just because, sort of teenage thing going. All right. Mu as a numerical value is telling you about the size or relative difference in electronegativity of constituent atoms. Basically, how big is that charge difference? It is a vector. That is, it not only has a number that says how big it is, it also has a direction or orientation. So the direction it goes always from less towards more electronegativity. Just like oxygen is negative, it's always pulling electrons in. You consider this to be sort of like an electron magnet. It has a magnitude, and that's the sum of all the little charges, all the little dipole moments that are in there. Why do we care? Well, I'm not going to make you do the mathematics on this, but I want you to get the idea. These are the ways people describe how big those charges are, and therefore they're describing what's likely to happen. So carbon dioxide, CO2. Let's do an experiment. Look. Ooh. CO2 and onions. I'm assuming you have more pure CO2 than I do. All right. Like, look, this is a negative oxygen. This is a negative oxygen. But look, they're exactly opposite each other. So in terms of the overall charge, they actually cancel out because they're pulling in exactly opposite directions. You know, just imagine Bavik and me playing tug of war with a piece of rope. Now, I know you think he's going to win. Half an hour ago, I poisoned him. Sorry, Bavik, just a bad example. But end of the day, if they cancel out, the charge is zero. Shape counts not just for reactivity, steric hindrance, and having to get to somewhere to react. Shape can also effectively neutralize the charges. Little water, H2O. Negative, slightly negative oxygen. It's an electronegative center. It's pulling electrons towards itself. A slightly positive hydrogen, a slightly positive hydrogen, and it has a shape. It does not cancel out. Its dipole moment is 6.17 Coulomb meters. For those of you who are in electrical engineering, you guys are all electrical engineers. Dr. Kong, you're an electrical engineer, right? What was your first degree? Then you branched off into medicine. Nice. Yeah, I find people with those weird interdivisional degrees, it's tough. So the shape here, charges, wildly changes the properties. Not just for reactivity based on shape and access to the site, but because the charges themselves change how these components behave. When we talk about the polarity of solvents, they always use a value that looks like a squishy, weird E. It is called the dielectric constant. Do you guys take physics?
Yes.
Yes? No?
Last time.
Yeah. I used to teach physics. I made people go outside and throw objects and do math. It's cruel. You know why? I'd make you do it in the snow. I can see what you're thinking. Dr. Manuel, thank goodness he didn't teach physics. Yeah, you're probably lucky. All right. We call it dielectric constant. What it measures, and this is a big idea, a measure of the solvent's ability to reduce the lower those interactions between charged molecules. It could increase it or it could lower it. In this same physical structure here, although you will not remember this from physics, it's the same thing we use for the gravitational constant of universal bodies out in deep space. It's the same equation. Closer things are together, R, the separation, you get a different or larger energy involved, and you have two charged particles. This is the law. All of these things, you have a higher dielectric value, lower energy, and reduced interactions. So at the end of the day, that dielectric constant that you can look up online or in a book is basically telling you about the polarity of that if you choose to use it. And a good thing to remember is maybe I should be using a solvent that has similar polarity to what I want to work with. You know, trying to work with, say, do a reaction in oil with water, it's not going to work. It doesn't have to be that obvious. It can be much, much closer and still not work. So in fact, getting charges and dielectric constants to be in the same ballpark is a fairly important thing. Most established standard procedures have long since done this. This is old. Example, acetic acid, CH3COOH. Have you guys know acetic acid? You ever had French fries? Did you put glacial acetic acid 1% solution on them? That's vinegar.
Vinegar.
Was it good? Do you have any right now? I'm seriously hungry. Yeah, its dielectric constant is 6. Formic acid, which doesn't have a methyl group smoothing things out, just another proton, its dielectric constant is 60. Formic acid is a much more polar solvent. So you can see that having things attached wildly dissipates charge and affects how those charges behave. Finally, donor solvents. That's a solvent that you pick that will donate unshared electron pairs. They're good bases, and we're going to come across that in examples a little further in. Let's see, should I put this in here right now? Let me just take a look. Yeah, I'm going to go and I just want to finish this with you guys today. I've asked for lots of time to do these lectures because I want to be able to go slow if we have to cover stuff off, and we're probably going to lose some days to holidays. But we got 16 weeks in total. There's no problem getting through it. I do not want to overtax you. You know, you can't actually eat 3 turkey dinners. What's that? You can? Carlo, that's pretty impressive. Yeah, all right. A couple other methods that people do substitution with alcohols. These are specialty reactions. The reason I'm putting them here is in industry, these two are very common. The way it works, this is little tiny primary and secondary alcohols, we want to make, for example, an alkyl halide. And it's also an example of chemistry Dave hates. I'll demonstrate. We use thionyl chloride, which you simply purchase industrially, ClSO, or you can use phosphorus tribromide, which is BR3, PBBR. So here's the part I don't like. And as a chemist and a steward of the environment, it's up to you to catch this kind of thing. Here's our 1, 2, 3, methyl, ethyl. Is it wethyl? Is it?
Propyl.
Chocolate cake, nice. And we've got monstrously negative groups sitting here, dangling in space. I wonder where they're going to... Oh, look! We've done a very simple substitution of a big negative item. That's easy. It is 1, 2, 2 chloro, 1, 2, 3 propane. Here's what I hate. Just made sulfur dioxide? You've literally made acid rain? Are you kidding me? What is this? The Dark Ages? Are we all going to go home and get bubonic plague? Man, that's bad science. Having worked in environmental chemistry for many years, I don't like that. Again, I wish to remind you, you can make a target compound. It is almost impossible to do without making lots of something else. And a good chemist will notice exactly what that something else is. Sulfur dioxide and hydrochloric acid, that's not terribly good chemistry. So I'll talk later on about ways we can do this, which are real easy, that don't involve such toxic chemistry. For example, you understand yeast will do this literally for free. Alexis? You've never heard of Cabernet? Are you serious? A tough crowd. Questions or thoughts, you guys, on today's stuff? You know what? You're scaring me. I'm beginning to believe the only thing you're going to remember is chocolate cake. It was blah, 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 chocolate cake, blah, blah, blah. Am I wrong? Let me just go back here. I just want to make sure that we're super good with this. You could also say these 4 properties are the properties that affect reactivity, right? If you add protons, you're going to make a positive circumstance. You're automatically making it susceptible to nucleophilic attack. You're the organic chemist, and you're choosing to set it up. If you add base, you can strip away protons. You can make negative areas that are going to react with electrophiles. Not a fluke. You're setting it up. If it can form hydrogen bonds, ready? It will. Easy peasy. This is no surprise. It's what's holding your DNA duplex together. And finally, that shape has a couple things going on. If it's a shape, generally, it can limit access to the reaction point. We call that steric hindrance, shape-based blocking. Stupid truckers. Shape-based blocking of access to the reactivity site. On the other hand, that shape, if it has a charge and is causing electrostatic interactions, means it's no longer interacting with itself randomly. It is no longer interacting with things you put in there randomly. Shape and charge change the properties of the liquid you're working with and the things you put in there. Chocolate cake. I don't actually have any cake in the house. I think I got muffins or something. That's pretty sad second, I guess. Questions or thoughts, you guys? Is this your last class of the week? It's literally your last class of the week.
Yes.
Yeah.
Yes.
Yeah, it's not mine. I got a bunch of meetings and got a bunch of stuff tomorrow. And then on Friday, it's my Omicron research group. We're now looking at the BA2 variant like crazy. Yeah, we are going to get through this. Not a big issue, unless you're unvaxxed, elderly, or don't like being sick. The parts that are disturbing is the data we've seen on the long-term COVID stuff. There just isn't sufficient clinical data, and it's not all being recorded the same way. Generally, we're going to get through this, and then I shall be able to nag you in person, which will be even less fun than me nagging you online. Although I do want to notice, folks, that by having a class start at 1 p.m., Polly is able to attend without actually being in bed. That's right, you heard me. Okay, you guys, have a nice evening. I have noticed it's going down to minus 35 below tonight. So either put your horse in the barn or plug in your car if you have one. Just saying. However, Monday, Tuesday, high of 0. My GPA in the last 2 years of grad school. All right, you guys, going to stop sharing. I'll let you go. Get rid of this. What a bunch of clicking. There's no easy out of here button. Okay, folks, take care. Cheers.
Thank you.
Thank you.
You.
Bye now.